So as mentioned in the last video, let's look at a handful of examples here involving friction. This is a kind of a common example you'll find in a lot of statics textbooks. We're going to put a ladder against a wall and against the ground here. And we're going to put a person out here on this ladder. I'm going to draw my awesome people drawing skills. Nice little stick person there on the ladder. I know, don't laugh too hard. What do we got here? So again, we got a wall and a ground, and we're going to say that up here at point A on the wall is going to be smooth. We're going to assume that this is roughly smooth. And down here on the ground, we're going at point B, we're going to assume that the coefficient of static friction is 0.35. We're going to say that the ladder has a length of 15 feet. We're going to say that the angle here is 55 degrees. Could have drawn that a little less busy, but here we are. And so what we want to know then is how far up the ladder can the 100-pound person, very light person, how far up the ladder can the 100-pound person go before the ladder slips. Maybe they slip before the ladder. That's another discussion. Let's say the ladder slips. Okay. Well, looking for a distance. Going to be involving forces. Anytime it's involving forces and looks like an equilibrium type problem, that means we're going to use equilibrium equations. Free body diagram is a powerful tool to help us write equilibrium equations. Some of you guys are figuring this out, I think. Yeah, a lot of the simple problems you don't have to draw a free body diagram for. You can do it in your head. We're rapidly moving away from some of the simple problems, and now maybe some people are struggling because you haven't practiced drawing free body diagrams with the easy ones. Stop by, let's talk about it. Let's get you what you need. What do we got here? I've got a vertical surface at A, so I'm going to have a horizontal normal force at point A. I've got a horizontal surface at point B, therefore I'm going to have a vertical normal force at B. And then I now have this friction force at B. Notice the way I've drawn it. Why might I draw it that way? Well, think about what's going to happen in this phenomenon here. And here's where we have to start thinking like an engineer and say, okay, well, how's this going to work? What's actually happening here? This person's going to climb out here. At some point, they might hit a point where this is going to go this way, and this is going to fall down that way, right? Well, this one's smooth, so there's nothing really holding this up. We don't have to worry about the direction of friction there. It's not technically smooth, but that's another discussion. But what they really only want you to worry about is the friction on this horizontal surface. So if this thing is going to fall, what's it going to do? It's going to slide this way. So point B is going to go to the right. That means friction needs to oppose that. Friction is going to go to the left. That's how we determine that value there. Now, what do we know for distances here? Well, what we do know is that from horizontal, this is a 55-degree angle, and we know that this overall length is 15 feet. Okay, so the overall length is 15 feet. So let's just do sum of forces in the x. Should be able to do these pretty quick. I'm going to have A minus friction B. Sum of forces in the y, I'm going to have, that's going to equal 0. I'm going to have I'm going to have B, I should write the positive first, positive B minus the 100 pounds. Okay. Now, that's two equations. Now notice I don't know this distance d. And we might come back to, okay, what is it exactly we're looking for? We're looking for this distance d. How far out on this ladder? Realistically, like, we're actually looking for this distance. We're looking for the distance along the ladder, but to find that, I need to know this distance d. Okay, so let's find distance d. I need to know how far out along this ladder this person can go before they start falling, before the equilibrium equations no longer make sense. Well, sum of moments about point B, I'm going to pick B because I got a bunch of unknowns at B, so I'm going to pick B. I've got A is causing a clockwise motion. This 100 pounds is causing a counterclockwise motion, so we'll start with that. I've got 100 pounds causing a counterclockwise motion at some unknown distance d that I'm looking for. Okay. And then I've got A causing a clockwise motion, so minus A. It's not at 15 feet, but it's at 15 feet. And let's see, I will need the vertical dimension. So it's going to be, and I've got the 55 degrees, so it's going to be the sine of 55 degrees. Because what I need to know is this vertical distance here, So that's going to be opposite of 55 degrees, sine 55. Okay, so let's take a step back and say, okay, what do we got? Well, I've got A, F, B, and D. I've got four unknowns. But remember, if we go back and look and say, well, what are the situations we might encounter? The object's not moving. Well, no, actually, that's not what we have. We have the situation where it's just starting to slide. So our friction force has reached this maximum value, the normal times that coefficient of friction. Well, B is my normal. FB is the friction force, so we can say that FB has reached its maximum value, mu sub s n. They've told me that in the problem statement. Again, don't assume this until they've told you something in the problem statement. If they're slipping or sliding, then that right at the instant before they do that, and I shouldn't say n, I'm sorry. We'll just say this, mu sub s b. The normal force at point B, we're just calling B. You could call it NB if you like. It's not going to bother me at all. Okay. Call it NB. We're just calling it B. Okay, 4 equations, 4 unknowns. I know mu sub s. Now we just solve. Right? So go ahead and pause here and solve and see what you find out. All right, finishing this problem out. So these are my equilibrium equations. Right? I said solve us out. So I'm going to solve, I'm looking for the d value. So I'm going to solve for d from the moment equation here. Right? I've got a 15, sine 15, blah, blah, blah. Right? Now this is what I know. Back up here, I know FB is equal to A. So I can plug in for A, I can plug in FB. That's here. Right? So plug in A for FB for A. And then I also know for FB is equal to mu sub s b because we're right at the point where it's starting to slide. So I'm going to plug in, we plugged in for AFB, and for FB I plugged in mu sub s b. Static coefficient of friction times the normal force times the other thing that we've solved the moment equation from. That gives me the distance d from point B to that location. Now, B is still unknown, but remember, if equilibrium is achieved, that means B has to counteract the weight, so B has to equal the weight. So notice I plug in mu sub s times the weight, 100 pounds, times the other things. Notice the weight cancels out. If you look at this problem in the textbook, often they will not give you the weight of the person because it doesn't matter. You're supposed to be mathematically mature enough at this point. I chuckle because I know some of it's myself sometimes included. I looked at this problem initially and I was like, I need to know the weight. Well, what if I just guess a weight? And that's what I did. Honestly, that's what I did. I said, what if I just plug in a random value for the weight and see what happens mathematically? And what happens mathematically is you get to a point where the weights go away. This distance, believe it or not, doesn't depend on the weight. It only depends on the friction and the angle and then the overall length. It's going to be some fraction of this length depending on the static coefficient of friction and that angle, believe it or not. It's kind of weird. But yeah, the weight goes away. It's interesting. Doesn't matter how much the person weighs, in theory. All that matters is this coefficient of friction and the angle at which that ladder is up against the wall. So, calculate it out. Now that's the value. I've got 0.35 as my static coefficient of friction back up at the very beginning there. So I get that this distance d, right, this distance d, again, this person is some distance from point B horizontally up the ladder. That's distance d is 4.3 feet. What I might really want to know is how far up the ladder they can go. Right? And turns out just for this angle and this static coefficient of friction, you end up halfway up the ladder. Now, I think that changes depending on the angle and the static coefficient of friction, but in this case, mathematically, you end up halfway up the ladder at 15 feet of this, 7.5 feet of this 15-foot ladder. But again, that's always interesting. The weight doesn't actually impact this answer. All right, that's one example. I'm going to go ahead and stop because I can't get another example done in less than 4 minutes. So we'll just throw another example in the next video.